All right, guys, good afternoon. We are going to continue and finish the topic of Newton's laws today. The last section of chapter 4 is to introduce frictional forces and the use of the normal force. But before we do that, I want to go over a few situations that are in the textbook. And one of them will be in the web assigned. One of them is the elevator situation or problem. All right. So for an elevator, there are two cases. You have the going up or going down, and the forces are acting are the same, but the way you think about the problem, the way you write the equations, changes. So in this situation, you have a person who is standing on a scale. Scale is what we use at home or in the airport to measure the mass of a luggage, right? In this case, this scale is reading the amount of force, right? If the person was on the ground, right? If the person was on the ground, the scale will read the normal force, which is the same as the weight, right? For a person who is not moving, just standing on top of a scale, the scale always reads the normal force. And a normal force equals to mg for a static case. But we have here an elevator going up. And the mass of the person is 65 kilograms, like an average person, but the scale is reading 840 newtons. So it's easy to compare these two and realize that the scale is not reading the weight of the person. The scale is reading more. Why? Because of the acceleration of the system, in this case, the elevator. All right. So in the case of the analysis for the person, right, you have the normal force and the weight of the person, mg. Those are the only forces acting on the person. And like I said, mg is equal to the normal when the body is on the ground, moving horizontally without any upward force acting on it. All right? So in this case, there is another force, which is this. So the mass of acceleration is the resultant of the difference of these two. Now, since you're going up and you guys have been on elevators, you know the feeling of going up is different than the feeling of going down, right? When you go up, you do feel sort of an extra force, maybe minimum, but there is an extra force sort of going up. That's because the normal is a little bit greater than what your body is exerting on the scale. So the resultant of these two forces is written like this. Normal minus the weight of the person, all right? So this is the normal force. Okay, it's right in there. So normal minus the mg equals to the mass of the person times the acceleration. Okay, so the normal is what the scale reads. So the scale reading, right? The scale reading, that is the normal. So I will write the equation 840 minus mass times gravity, which is gonna be close to 650. Yeah, 637, equals to ma, which is 65a. So we can find the acceleration of the elevator. Okay, so that minus that is 203. So 203 newtons is 65a. So acceleration is just 203 divided by 65. That's 3.12 or 3.1 meters per second squared. So there you are. You find the acceleration of the elevator by using the reading of the scale, right? So that's a situation there. Okay. An elevator going up. What happens if the elevator is moving downwards? Logically, we have the same forces acting on the person. Normal, mg, that's the scale there. The mass is the same. But now they give you the acceleration. Now they tell you that it's going down at 4 meters per second squared. Logically, what your body is going to exert on the scale is going to be greater than the normal. That's why now we write it like this. mg, so your body's weight, minus the reading on the scale, equals to your mass times acceleration. So we're giving the acceleration now, so we want to see what the scale is reading. So this was 637, right, from the previous example, minus the normal, equals to 65 times 4, that is 260. So the normal goes here, and this goes to this place, so that's 7, 5 minus 2, 377. So the normal is way less now. Again, makes sense because since now you're going down, your body is exerting more force than whatever the normal is. Okay? So that's the normal for, or that's the scale reading, right? That's the scale reading when the elevator is going downwards. All right, so there you have it. That's a situation there. Okay. You could do this experiment. I've done it. I've done it with, as a demonstration years ago. You can just get a scale, like, the one you have in a bathroom, maybe, and put it in an elevator. If you have an elevator, there's an elevator in the building, right? You can test it there. When you go up, when you go down. I mean, of course, it depends on the scale, how accurate it is, and the scales that we have read masses, right? It's in kilograms. But still, like for example, this is approximately 37 kilograms, right? So a 65 person is getting this reading. And the same person, when it's going up, is getting it was getting 840. It's about 84 kilograms. Now, these may be less or more depending on the acceleration. So elevators may not go up at 3.1 or 4 meters per second square. They may go at a lower acceleration. The lower the acceleration, the less the difference. So for example, if this was 1 meter per second square, right? The difference between the normal and the weight is only of 65 newtons. So that's about 7 kilograms, right? So you will see the difference, you will see it, but not as much as in this case, all right? So that's the situation I wanted to go over. Again, it's on the web assign. I believe it's here. It's problem number 4. So now you know how to do it. And then we'll have to talk about friction. But before we go into friction, let's show you. Well, I have the drawing here, so it's from the book. There. So they give you a pulley with masses, right? One on an inclined plane, one hanging like this, and they're asking you to find. So in the following, oh, by the way, the following system compute the value of the acceleration and the tension on the rope. I finished today, between yesterday and today actually. I finish exam number 1. So exam number 1, which is going to include chapters 1 through 5. So we're finishing 4 today. We start with chapter 5 on Monday. So that gives us Monday, Tuesday, Wednesday. That's enough time to finish it. So exam number 1 will include all those chapters. And it's not going to be like the quizzes that we've been taking. Like I said yesterday to a few students, that day, you guys are going to just come in on Zoom. I will take attendance. And I'm not really going to proctor it probably as much. I will still be on the Zoom for a bit. But you guys are going to have to download the file and work on it and then submit it by the due time, by the deadline. All right. I have 9 questions for that. Yeah, 9 questions I have for that exam. And then I will give you some details, but just so you know, it will include chapters 1 through 5. So everything we're doing so far, plus what we do Monday, Tuesday, and a little bit of Wednesday next week. All right. So pay attention to these situations. Like for example, a problem like this, there is a similar problem like this in the exam. Okay. And also, I mean, you can find one like this or even like this in the assignment, right? On the textbook, if you have it, I took this problem from the textbook, by the way. All right. So how do you do this? So this is a two-body problem. And yes, all the questions in the exam are all open-ended. So that is how tests are. Okay, quizzes, we combine them, and the final exam is all multiple choice. But tests, major tests, the free major tests, all of them are open-ended. Okay. Let me answer something here as well. There's somebody.
So we're finding the acceleration right now?
Yeah. Yeah, we'll start the program. Just answering some students are asking questions here. Okay. So you have to do your free body diagram, all right? But like we did yesterday in class, you want to use some of the physics, and there's no friction, all right? So if there's no friction, logically, this mass is going to go down. The 10 kilogram, because there's more mass here than here, and this mass is going to go up with an acceleration that you want to find. Like that, and like that. Okay? Gravity, still a factor, right? Never forget. And the pulley is ideal. So For the 10 kilogram mass, that's an easy one to begin with. You have the rope is hanging. So what forces are acting on the 10 kilogram mass? To put some ice here, I think.
Weight and tension.
So the weight and the tension, right? We draw it like this. It's an extensive force. 9.8 for gravity, so that's 98 newtons. And that's tension here. What about for the 5 kilogram mass?
49 newtons. The weight.
Yeah. And what else?
Normal force.
Normal. And
The tension on the rope.
tension, right? Yeah. What's this? All right. Why is the 10 kilogram going down? Because of this, but there's tension, right? So, like yesterday we did, what will be F equals to MA for 10 kilograms? That's the equation we have to use. So for 10 kilograms, what will be Newton's second law? Remember that it's going down. 98 minus, don't forget the tension, equals to 10A. So for this one, it's easy. That's like the Atwood machine that we did yesterday. For the 5 kilogram, you have to be careful though. What is the equation for the 5 kilogram mass? Okay, you see the weight is acting like this, the normal is acting like this, but there is an angle of 40 degrees. This mass is on an inclined plane. So
So we do
we
uh the sine 60 of the for the gravity.
yeah, so we have to
I mean sine 40, my bad. Sorry, sine 40.
yeah, we have to extend this. This is 90 degrees, 40, 50, 40 here, yes. So this is the angle, and because we're using this angle, this is the adjacent, this is the opposite. So yeah, this will be mg, which is 49, 49 sine of 40. There you are. So you have a force that is dragging the mass downwards. But overall, 5 kilograms is going upwards on the plane, on the slope. So tension is larger. Yeah, tension minus 49 sine 40, yep, equals to 5A. Like that. So we have again two equations with two variables, but because of the problem itself, we always get this, right? Like this. Oh, okay, I was waiting for that. Let's do this thing quickly. Actually, I'm gonna let you guys do the math and you guys get the answer. Because I did this before. I did this yesterday a lot. So you guys finish with this. I'm gonna write here. Find the acceleration and the tension, then we can compare answers. All right. Come on, guys. Finish it. That's for acceleration or for tension? The 4.43. For acceleration, yeah, I think that's right. Let's do this. 40 sine times 49, 31.5. So this will be the equation for acceleration, right? If you add these two, this cancel, and then you get this. So yeah, it makes sense, about 4.43. Yeah, so you got it right. And if that's the right, then that's about 40. Tension should be about 50. Like, we're talking about like what? Like 54, right? Is that what you guys got for tension? Because the acceleration is this minus this. That's about 60 or 50 something. Right? Divide by 15. Well, 4.2. More like 4.2. 4.2 meters per second square. And the tension, if you substitute this in here, that gives you 42. So 56. I get those values. I don't know how you guys did this.
I got 53 newtons. Is that wrong?
I got 53 too.
53. Oh, shoot. 31. 35.5. Okay, so that's 31.5. Okay. So yeah, this is 31.5. My bad. Okay.
For newtons, I got 53.7.
So 4.43 right here. And then this will be 53, you said?
53.7.
Okay. There. All right, so that will be the answer for this. All right, similar to other problems we've done before. What makes this easier so far is that we are ignoring friction. Okay. I think now this is more clear. The concept of free body diagram, forces, acceleration. All right, now we are going to finish the chapter by expanding. So we're going to continue doing examples like this, right? There's some examples here. But now we are going to add friction. All right. So it's not much to add. It's just a little bit of the concept. And you're going to understand more of this when we do the examples and the practical on campus. All right. Which is basically going to be doing an experiment using masses on a rough surface. Okay. So basically a more realistic case, right? Because friction is actually always happening, all right? You can experience it just by walking. The reason we walk, the reason objects don't keep traveling forward or backward or up and down, is because of friction, right? You can view this as I said, as a surface that is not completely smooth, but is rough. And we quantify the friction on a given surface with a body in contact by what we call a coefficient of friction, which we label it like this. Now, we're gonna eventually gonna call it mu or mu k, but so just so you know, there are two. There is mu k and there is mu s. So what is mu k, and mu s? That is a coefficient of friction, or in this case, mu k, coefficient of kinetic friction, which is a dimensionless, so it doesn't have any units, right, or unitless quantity, which is a property of the material, right? So there you have typical coefficients of friction, which are normally less than 1. Right, between 0, 0.1, and 1. Now, there are cases, especially for static, where they can be greater than 1, but that's odd. Normally, coefficient of friction is less than 1, about these values, all right? And clearly, if you're on ice, if you're on wax surfaces, right, the friction is really low, but never 0. You can ignore it and you can get a good approximation of acceleration, or like you guys noticed yesterday, you can ignore friction and still find tension, masses, forces in equilibrium. But there is always a tiny difference, and that is because even though you can have ideal pulleys and assume that there is no friction and have everything ideal, there is some friction that will introduce some sort of error or difference, okay? So the way you find the frictional force or force of friction is by multiplying mu times normal. So now is when the normal becomes relevant. So we are even going to redo some of the problems that we've done so far, like for example, this one. We can redo this example by adding friction between the 5 kilogram mass and the inclined plane. And the only thing that you have to be careful is with the with the direction. All right. Now, why do we have kinetic friction and why do we have static friction? This one. Okay. So the static friction is what keeps an object from starting to move. And the best example is an example from home, right? Imagine you trying to move furniture at home. It can be a desk, it can be the fridge, it can be your bed, right? In order for those bodies to start moving, right, you need to exert some sort of force, right? The static friction has a maximum value, and it depends on how much you need to keep the sum of forces 0. Now, if you start moving a body from equilibrium, right? So for example, if you try to push or pull your desk, and after some effort, you finally move it, you are breaking the inertia. You are basically exerting a force that is equal to the static friction and eventually greater than it. That's why the static friction is normally greater than your kinetic friction. And you can see that from the mu's. So your static friction, the mu, is always greater than the kinetic. Why? Again, we can use real life for this, right? Once you start moving your furniture, and you probably have experienced this, right? Once you have started moving a body, it's easier to continue pushing it or pulling it. It's like you need less force, right? You still need some force, but less than when you try to move it on the first place. That's because as soon as you break the static equilibrium, so as soon as the body moves, the friction lowers. So it's easier. You require less force to keep it in motion. All right. Now, in most of the examples, we are going to use kinetic friction. Why? Well, because we are going to have, in most of the cases, bodies that are moving. All right. So the take-home equation here is this, that the kinetic or friction in general, so I can write that here, right? What's that? So we can have that the friction. So normally we draw it like this, friction with a lowercase f. That's equal to mu n. And if we divide this into static friction, and then here kinetic, the equation is Fs mu s times normal, and here Fk mu k times normal. Okay, that is the take-home equation, right? That's the main thing about friction. And then at the end of the day, this is what matters, is how you compute the normal. In some cases, it's easy, like the one I'm gonna give you right now. In some cases, it's not. So you have to be careful, all right? So now you have another parameter that you have to sort of worry about, okay? So let's do the example. It's 6:40 already, really? Let's give you a mass on a table. Like that. Like that. We have a mass on a table, and now they give you, or I give you, a coefficient of static friction of 0.75 and a kinetic friction of 0.45. The mass, let's say, is of 40 kilograms. Okay, let's keep it a whole number there like that, round it. So the question A, what is the minimum force required to move the mass from rest? B. Once the body starts moving, what is the acceleration if you keep it moving with a constant force of 215 newtons? All right. Oh, no, I cannot do that. To find the minimum force required to move the body from rest, you need the static friction. Because the body is not moving, it's just there. So if I do the forces diagram, you have the weight, you have the normal, and now, because of this, you have friction, and the way you draw friction is like this. No, it's not moving, right? So we use the static friction, Fs. The weight is 392, right? 40 times 9.8. So because it's just a body in a horizontal table for part A, the normal force is equal to the weight, which is 392 newtons. Therefore, the static friction is mu s times normal. Mu s is 0.75. Times normal. So my static friction is 294. Guess what? That is the answer for part A. So the minimum force required to move the mass is 392 newtons. Because that's the value of the static friction, 294 newtons. Because that's the value of the static friction. Okay, that's how you use static friction. A static friction is only used for bodies that are about to move. So a situation like that, a question like that, okay. Any questions? How will you do part B? Once the body is moving,
Just a small question, Professor.
okay, yes.
Usually in questions like these, right? Like questions like this, the static friction and the kinetic friction, the values that you gave us, those would be given, right? So based on that, we find the friction, right?
Yeah, in most problems with friction, mu will be given,
Mu.
unless they ask you for it, right? But yeah, mu is normally a given value, and you work on it to find friction.
Okay.
Yeah, part B. So part B will require kinetic friction because now the body is moving. When the body is moving, you use kinetic friction. What is acceleration? If now the force, and look, the force is not 294, it's 250 only. So it's less force. So how will you find the acceleration on part B?
We'll use the kinetic energy formula.
Okay, so what force we have to add now here? Yeah, F minus friction equals to 48. Very good. Where F is 250. So you have this. So the equation for B will be 250 minus Fk, it's kinetic now, equals to 48. Fk, the normal is the same, 392, but the mu is not 0.75. The mu is now 0.45. That's equal to 48. Okay, what do you get for acceleration? If you use that equation now. Nobody got it yet? Or you still working on it?
Still working. I got an answer here, 1.84. Is that right? It makes sense because of the friction. It has to be like low. I got that.
Okay. So simple situation, guys, because you just have a mass on the horizontal there. All right. Is the normal always equal to the weight? No. Let's do situations where it's not. Are there any questions about this?
So kinetic energy is for when it's being dragged, and then the kinetic friction is for when it's being dragged, and then the static friction is for like the bare minimum to move it.
Pretty much. That's basically it. And like I said, most of the time we're going to use kinetic friction. Like the following examples we're going to do. This one here. So let's read this. It says if a 300 Newton force, so F is 300, is acting on a body like this or like this. So I think there is, this one here. So first you have a 300 Newton body, right? Push across the floor at a constant. Okay, let's see. So now this one here, right, is being pushed at a constant speed by 300 newtons, an angle of 20 degrees below the horizontal. So this angle here, yeah, below this one, I mean, but yeah. What is, okay, look at this. What's the coefficient of friction between the crate and the floor? All right. So constant speed, that's important. Direction here. And you have to be careful with the normal here. All right. So situation A is this. That's what they're telling you, this figure. Yeah. And the force 300 and the mass. Oh, the weight. The weight of the crate is 1,000 newtons. Right? 1 times 10 to the freight, that's 1,000 newtons. So that's already the weight. Okay, let's draw it here. So Now what you have to be careful is gonna draw this. You have to be careful because now you have the mass the same, right? So that doesn't change. You have a horizontal ground, but now you have a force acting like this though, at an angle of 20 degrees here. This weight, they're telling you, is 1,000 newtons. And is moving at constant speed. So this is constant. What does that tell you? Oh, the force is 300 newtons. So let's put F here. And F is 300. And you want to find mu K. All right. What do you think you have to do here? What will be the first step? You already have the weight, so and you already have the force here. What other force is missing here?
Normal.
Okay. And is the normal the same as 1,000?
Yes.
No. Because you see the force? I want you to imagine, or you can even do it right now. What's easier? Like, try to do it right now with anything you have at home. Maybe your chair. Try to pull your chair or push your chair just horizontally. And then try to do it at an angle like this. What's easier? Horizontally or at an angle?
Angle.
No. Like think, when do you need to exert more force? At an angle or like when it's horizontal? You're pushing, not pulling, by the way. It's different.
I would say horizontal because if you move at an angle, it
Horizontal.
kind of goes forward, so it's easier.
Yeah. Since you're pushing it, it will be easier if you do it horizontally. So this force like that is giving you more friction per se. Why you're getting more friction? Because we have to do this. We have to break this force into components. And look at this. That's the horizontal one. But look at the vertical though. The vertical component goes down. And somebody's doing it right now. So fx2, yeah. So you want to find fx and fy. Let's call it fx and fy. But fy is going down. All right, that's important for this. So fx, I'm going to write here, is 281.9. That's what a student got. Check it, please. All right. Fx is basically 300 cosine 20. All right. So this is 300 cosine 20, which, yes, that makes sense. And then Fy, how will you find Fy? I have an answer here already. This. How do you find Fy though? What's the equation for it? 300 sign, very good. There. So why do we need this? Because fx is the one that is causing the motion. Fy, however, now we want to find a normal. So it's right here. So how do we compute the normal force? So you do this. 1,000 is only moving horizontally, right? Vertically, there is no motion. So whatever force is going down, which is 1,000, has to be equal to whatever force is going up. But down is 1,000 and Fy. So 1,000 plus this is equal to the normal force. Right? That plus that equals to that. There. So my normal force is 1,102.6. It's more than the weight. Is that clear? Or who has a question about this? Do we need to ignore gravity for it? No, you're not ignoring gravity. It's just that you're already giving the weight. So if you're already giving the weight, why do you need gravity for, right? All right. So be careful with that, by the way. Sometimes they do that in the book. All right. They give you the weight, not the mass. Any questions about this? The normal. So now I have the normal. I'm being asked for mu. If it's moving at constant speed, what's the value of the acceleration? If it's moving at constant speed or constant velocity, what's the value of the acceleration?
Will it be 0?
0. So let's write Newton's second law then. What's the force that is making it move horizontally? Fx. So 281.9 minus kinetic friction equals to m mass times acceleration plus 0. So that's 0. All right? 0. What's Fk? Mu k times the normal. So that's the normal, right? So 281.9 minus 1102.6 times mu, that's equal to 0. This is how you solve for mu. So 281.9, I send this to the other side, 1102.6 mu. I divide by 1,000 on both sides, right, by this. So mu is very small, actually. What's mu equals to? 0.26. No units. That's my value of mu.
We have a
Now let's see
question.
let me see this. 0.256. I mean, they use fix, I guess. That's what's your question?
I don't understand where we're subtracting the normal force times mu.
This part or this part?
The second.
This?
Yes.
So you're finding the net force. The net force acting on this mass is the force moving it to the right minus the friction. Yeah, sorry, I forgot to draw that here. That's the friction here. That's Fk. So Fx minus Fk equals to mass times acceleration, but the acceleration is zero because it's moving at constant speed. So that's
Okay.
why I have this minus that equals to zero.
Okay, thank you.
There was a problem with friction in the quiz today. I changed it because I thought I should have left it because it's not that difficult. It's the same as you guys have been doing. Okay, so part A, we just check it, it's fine. Part B. Okay, so now we have to do part B. So part B is different though. It's the same idea, but now you are pulling. So instead of pushing, now you are pulling with the same force at the same angle, but now it's above, right? It's 20 degrees above the horizontal, uh like this. What will be the acceleration? Okay, so now you want to find the acceleration if you assume the same friction as in part A. So now, I wish we can just copy paste this. All right, so let's do part B. So you are going to draw the table, the mass here, the same weight. I want to let you guys figure this out for a bit, okay? Because it's the same idea. The only thing I want you guys to pay attention is that now this is the same force, but now you have here going up 300 newtons. That, and then mu is this mu, right? So this is mu equals to 0.256. So you want to find the acceleration. All right. My hint is that the normal is affected by just like this. But I want you guys to pay attention at the direction though. So your normal, you have to be careful, and then we use the same Newton's second law, all right? If you have questions, you can use the chat, right? If you are doing the problem, you can ask me, like, if you're in the right track. Yeah, so this time the normal is gonna be, you're gonna subtract it, yeah, exactly. It's gonna be less than before. That's why it's accelerating. Okay, so I have an answer already. Anybody else? So 0.5. 0.5 seems realistic. Anybody else got an answer? Who got like the acceleration of this? Let's check actually what you got. Yeah, you got it right. 0.5. So does anybody want to so telling me what you guys did? So we have the normal is gonna obviously draw that in here. What do you do after this? You find fx still goes to the right, but if y changes, right? If y is going up, yeah. So look, they are going up, normal, and fy, and the weight is going down. So fx and fy are the same, this is the same angle, so it's gonna be the same as before, right? So fx is 281. Let's just use the same 281.9. And fy is 102.6. Newtons. Okay, so how do you find the normal now?
So we add the weight plus the fx plus fy.
So what will be your equation to find the normal?
It'd be 1,000 plus 102.6 plus 281.9.
No, so you cannot use this anymore. This one was for part one. That's the normal for part one. That's done. For part two or part B, vertically you have 1,000, you have fy, and you have a new normal though, going up. So this normal plus fy, they both are going up. That's equal to the weight. The weight is the only one going down. So what you obtain in this problem is that the normal is now less than the weight. Before it was 102.6. Now the normal is 1,000 minus this. 897. Okay, physically, right? If we use, let's do the science of this. Can somebody explain me why the normal is less now than here? Here the normal was this. Now for this case, when the force is going, when you are pulling, the normal is less. Why? And I think I told you this before. You do this in real life. When do you pull objects like this? The force is pulling away instead of towards, so the object does not need to fight hard. Yes, that's good. The force, when you pull it towards, the object does not need to fight harder to go into the ground. So when you are pushing the body towards the ground. Ergo, you are increasing the normal. You're increasing friction. When you are pulling, you are trying to lift the body. You're not lifting it, but you're trying. So you are reducing the normal. That's why we move luggage at an angle. Now you know why you do what you do. I mean, not many people stop and think, hey, why do I do this? Just do it. But now you know why luggage is designed in such a way that you can pull it diagonally, because that's how you can reduce effort. All right. All right. So that's my normal. I haven't finished yet, right? We have to find now the acceleration. Fx, 281.9. So I have the equation here. So 281.9, very good. Fx minus the friction, which is mu. Mu was 0.256. Mu times the normal, which is A 97.4. That's equal to mass times acceleration. Okay. The mass is 1,000, though. The weight is 1,000. What's the mass? A 1,000 over 9.8. You divide by 9.8.
102.04.
Yeah. So let's do the math here. 0.256 times 897.4 minus 281.9. Okay, so I get 52.17. That's, you said 102.04, yeah. So 102.04 times the acceleration. There you are. So I divide both sides. 0.511, 0.510. So yeah, close, very, very good. So 0.511 meters per second square. It depends how we round it, but there you are. That's the acceleration. I want to give you guys a 10-minute break because you guys have a quiz at 8. I will do more problems when we come back, but that's basically what we're doing. We're just going through kind of the same situations we had before, but now with friction, all right? So yeah, we come back at 7:25 and we'll do at least 2 more, and then we start with the quiz, all right? I'll be here if you guys have any questions. I'll stop the pause this now. This is mg, right? 60 times 9.8. And then what else do I need?
You need a normal force.
A normal force, which is like this.
588 newtons.
A normal or this?
The weight.
Well, it's 509, right? If you round it. 509 newtons. Okay. Normal, let's extend this so you guys can see again the angle. It's 90 degrees, 30, 60.
Sorry,
We need
you
this
said
not
60
this.
times 9.8 is 509? I think
That's what they're telling me.
we
It's
get
588.
588.
588.
509 would be the force of x. The v of x, sorry.
Yeah, so that's where I wanna go. Now that we have the weight, you guys know that we have this force, which is causing the boy going down. But now we have the normal and we have mu. That means that now we have friction here. And it's on this direction. You see how I'm drawing it? That's Fk. So this force, like you guys said, is 588 sine 30. Which, well, you calculate that. What about this one here, though? What is this? I'm breaking into components the weight.
I got 509.2.
What? 588 cosine 30, right? So in the chat, they're telling me that this is 294. And what do you get for 588 cosine 30?
509.2.
509? Let's just... Okay. We have this component. Now we need this, huh? This one, we're gonna, we're gonna need because of the acceleration. It starts from right, by the way. For part A, we need to find the normal. What is the normal force equals to? N. What's N equals to? Look at the figure. So the normal is opposite to this. Normal is 509. Basically, mg cosine is a normal force in an inclined plane. And why do I need a normal? Because now I can find Fk. What's Fk equals to?
Is it
Mu k times
61.08?
61. Point oh eight is what you got. So 61.1 newtons. Yeah, that makes sense, right? Newton's normal. Yeah, that's good. All right. So, okay, so that's part A, basically. That's the answer for part A. That's the force of friction. We got this. How do you find the acceleration now? Part B. How will you find the acceleration? Okay. What's the force that you have to use now? What's making the boy slide? That one, right? Yeah. So 294 minus the friction is the mass of the boy times acceleration. So this is 294 minus 61.1 equals to 68. All right. .88. Yes, that makes sense. Meters per second square. That's the acceleration. Any questions? We did part A and part B.
I did have a question about like when we have to find this, when we have to use the angles, like we for A, you turn the triangle, you had the turn triangle 90 degrees, you had the other 30 degrees side in order to find the length. When do we know when to do that?
To do what? To find what?
You know, the 588 cosine 30. When
Yeah.
do we know when we have to use that in order to find
When
whatever
you're
we're
given
looking
friction.
for? When
When
given
you're given
friction?
friction. When you're given friction, you have to use that because that's the normal, right? We didn't use it before because if there's no friction, this doesn't play a role. But when you have friction, you have to use this because this times friction times mu is the Fk, the force of friction. And that reduces the force by that. You see that subtraction? That's why. So your net force is less. So your acceleration is less.
I also that's something I wanted to do. Like, just I wanted to use the iron production, all the coal.
What was that?
When we scroll up, I wondered. You drew the pink line to show that it's like a 90 degrees at the top, but what if we just like do the lines like, you know, the weight line that you drew that goes straight down for the force of the weight? Why do we have to make a cosine on the left? Why couldn't it have been sine? Because if I drew the straight line down, wouldn't I have gotten 588 sine 30 instead of 588 cosine 30?
Because you have the reason is because when you break into components, you want to use the angle with the horizontal. Like you have to realize which is the adjacent, right? So the adjacent to this to the weight is this one here. And the angle between the adjacent and the weight is 30 degrees. That's why we do this. The adjacent is mg cosine, and the opposite, which is this is the opposite, this one, this line here, which is this one here, is mg sine theta.
Okay, thank you.
Okay, that's why we do that. Okay, now we have to find okay. So we find the acceleration, we have the the length of the ramp, how do you find the speed when he reaches the end of the ramp? So V final. How would you find V final? You're not given time, so what equation will you use? That's like kinematics, huh?
You would use the v final squared equals v initial squared plus 2ax.
Yeah. Yeah, you want to use that. Two AX. B initial is 0. It's from rest. B final, you want to find acceleration. X is 20. So B final is the square root of 2 times 3.88 times 20. All right. 41. Yeah. Yeah. 12.46. Or 12.5 actually meters per second. There you are, guys.
Sorry. Where did we get the 20 from?
The length of the ramp is 20.
All right. Okay. Thank you.
All right, so that's another good example with combining, right? Forces, Newton's laws, friction now, and of course, kinematics. Any questions before we do the last example? Okay. Let's do this. Now you see how I did this. I want to guys let you guys work on this. Friction is 0.1. So mu is 0.1. Mu k is 0.1, 0.10. So the mass is moving upwards due to this force. It's accelerating, of course. What's the value of the acceleration? That's not bad. All right, so I have an answer here. Seems right based on the values. So what do we do? What's the first step in this problem? So you found this, right? $5.8 times 9.8. And then you found fx and fy. So basically this, look, I don't know if you notice this and this, but you also have this. Don't forget that there's also friction. Fk. So what's 5.8 times 9.8?
56.84.
56.84?
Yes.
Okay. Now, what's the value of this component and of this component? What's the value of this? This is mg cosine of 25. What's this? $29? Yeah, you got it right. And this is mg sine, the red one here. So this is, let's erase this for now. Let's put it here. Mu k is 0.10. So this one is mg sine of 25. Fk, what's Fk equals to? It's also going downwards. Well, this is 13.2, 56.84, yeah, that's 13.2, right? Yeah. So that's mg sine newtons. The friction is mu k times normal. What's the normal equals to? This is a normal, 29. Ah. So that will be 2.9. 2.9 newtons. So it's not a lot of friction because it's low. It's a very tiny coefficient, but still, this is 2.9 newtons. So what is the net force pulling the mass upwards? So let's write here. What's the net force acting on the body? Hmm? 13.50. So 32 minus 2.9 friction minus 13.2, right? The mg sign. That's a net force. $32 minus 2.9 minus 13.2. I get 15.9. Is that what you guys get for the net force? 15.9 newtons. I subtract the given force minus the friction minus mg sign. Now let's check that mg sign. Oh no, this was 24.02, so
So wait, is 56.84 sine 25, is that referring to the normal force, or is that a separate force?
that's the component of the weight dragging the body downwards. So this one has to change. So 32 minus 2.9 minus 24.02. That's equal to mass. Well, let's find the net force first. 32 minus 2.9 minus 24.02, 5.08. Yeah, 5.08 newtons. That's a net force acting on the mass. To find the acceleration, we know that the net force equals to ma. The net force is this. That's the mass times acceleration. What's the value of the acceleration then? 0.87? Yeah, 0.87 meters per second squared. All right, guys. So quite a few examples today of friction, steel with forces, Newton's second law, but now we have added that into the mix. On Monday, I'll do half the class, at least half the class of at least a few more examples of this. Web Assign has problems with the tensions, with the two bodies, the elevator, this problem that we just did, this one that we did in class, this one that we did in class, and this one I told you. All right. So do that to practice for the exams, gonna help you. Again, there are more problems in the textbook that you can always take a look for more practice. All right, so we'll do a couple more at least on Monday. And then we will start with chapter 5, which still is going to talk about forces, but we're going to introduce another parameter known as work. All right. Any questions about today? So I want to be grading the labs while you guys are taking the quiz. So we're going to start in 5 minutes. All right. So take 5 minutes to get ready. All right. Like last class, I will take attendance right now. Let's just use your camera attendance for like a couple of minutes, then you can turn it off. That's fine. I'll be here in the Zoom. Just double check. Some of you are not here today for some reason. I don't know. Yeah, so let's do this. Mhm.
Sorry, you said you wanted our cameras on while you do attendance?
Yeah, just for like a couple of
I've been
minutes.
getting so distracted. I think I get my body still. My God.
Professor, you haven't posted the quiz yet, right? Because I don't
No,
see
you
it. Okay.
no. I'll post it in a bit.
Also, since we finished lecture, I wanted to ask about you explained it to me, the trig thing, but I just didn't want to disrupt the class. Could I ask about it again for the last question? I genuinely I still don't get
Yeah.
it, like
For I guess this,
the
right?
last question. Yeah. I still don't get why we use cosine instead of like sine.
Uh, so you draw this, right?
Yeah. I got until that part and the other part where you draw the normal and
90.
then
Yeah, so that's the key. The key is that you have to draw the normal now. Since now you're drawing the normal is a force that is perpendicular to the ground and the body. That's the normal there. You extend it like this. So you have a right triangle here. Theta, 90 minus theta, right?
yeah, it'd be
And what's the angle here then? It's a right triangle here as well.
25.
What is angle that I'm changing right now? Huh?
It would be the same angle as theta, right?
Yeah. So now you are looking at the MG. This is the adjacent, and this is the opposite. This one here. That's the opposite, that's the adjacent. Make sense?
Yeah. Okay. Sorry, you
So if
said
that's the adjacent,
yeah, okay.
if that's the adjacent, this will be mg cosine theta. It's adjacent over hypotenuse is cosine. You see it?
Wait, sorry, could you say where's the hypotenuse of the triangle we're taking it from?
This is the hypotenuse. And this vector here could go here. So hypotenuse, adjacent, opposite. And this is the hypotenuse.
Oh, okay. I see it now. I think it's because I kept thinking the hypotenuse was the horizontal line on the bottom, or it was the opposite
Yeah,
line
you're
of the
looking at this
normal,
triangle here.
but Okay.
You're looking at this triangle.
Okay, that makes a lot of sense. Okay, thank you.
Okay?